my name is Elise Cheung-Sutton, and today I'll be talking about predicting solar generation based on weather variables. The question for this project is, can weather variables be used to predict hourly solar power generation in California? In 2018, 14% of California's electric generation came from solar, and 32% for all renewables. In the graph to the right from the California Energy Commission, we can see that renewables start coming in around 2013 in the green and yellow segments and have continually grown to what they are now. California also has a 60% renewable goal by 2030, so we can only imagine that these numbers will continue to grow. Thus, predicting supply will be crucial to system efficiency and cost effectiveness. The data used in this study for weather came from NOAA, which has 7 stations in California for which the data was downloadable. Obviously, weather for the whole of California is varied. Perhaps I could have averaged these stations, but I just decided to use the Bodega Bay station for simplicity since the coast has more moderate weather variables. The source of solar generation data was from the U.S. Energy Information Administration, EIA, and both of these data sets were 2018 hourly data in California, and they are joined by the UTC date time. There were 8,783 records, which is the number of hours in a year. There were 12 features to be explored: temperature, solar radiation, surface temperature, precipitation, relative humidity, soil moisture, and soil temperature. You can see in the chart to the upper right, the correlation matrix, that many of the variables were either very strongly positively or negatively correlated. So there was going to be some collinearity that would need to be explored. Also, some of the variables shown in the bottom right, their histograms show that there were a lot of very, very small values and very few large values. The first thing I did was to drop null data in the data set. For the weather data, null values were stored as strings with the value of space -9. And as you can see in the small table excerpt, that if one of the values had that -9, then many of those values did. So I just decided to drop those records because there were only 17, which wouldn't impact the number of records very much. Similarly, in the solar radiation feature, some of the values were 999 to signify null data, and of these there were 368. You can see in the scatter plot to the right, they very distinctly stand out from the distribution of the rest of the data. And so I dropped these because I did not want to make a bad guess as to whether the sun was on or off at a certain time of day. And because this feature was probably going to be very important to the study, I did not want to make a bad guess. The target column, which was solar generation in megawatt hours, had the range of 0 to 13,600. There was no missing data, but again, in the bottom left graph, you can see the histogram shows a lot of very small data, very small values, and not very many large values. And on the right, you can see what that looks like daily. The generation turns off when the sun turns off and then rises as the sun rises. I first explored feature importance with the RFPIMP package for linear regression. The chart on the top left shows something a little bit suspicious, where solar radiation is not the most important feature. So this suggested some collinearity. When the collinear features were removed, the bottom left graph shows that solar radiation is clearly the most important variable, with surface temperature also playing a part. Similarly, in the random forest feature importance, solar radiation consistently came up as the most important feature. When the collinear features were removed in the bottom right table, you can still see that solar radiation plays a significant role. The feature transformations I tried that increased mean absolute error in the random forest model were dropping the collinear features, which actually surprised me. So this signified that all of the features, even if they were collinear, were assisting the model's predictions. Scaling all the features, scaling only solar radiation, doing a quantile transformation on all features, and binning solar radiation also did not help. The one thing that did decrease mean absolute error slightly was quantile transforming the non-solar features. For model selection, I did a cross-validation of a selection of regressors. The ones that performed best were the random forest and extra tree regressors. I chose my metric to be mean absolute error because mean squared error penalizes outliers, and the values that came up were in the millions, so they were a little unreadable. Mean absolute percentage error is undefined when y equals 0, and I had some generation equaling to 0, so I did not want to use MAPE. I then grid searched the hyperparameters for random forest and extra tree. For a random forest, the best hyperparameter was to increase the number of trees and choose the criterion to be mean absolute error. For extra trees, decreasing the number of trees and selecting the criterion to be mean absolute error were best. I then used the candidate models with hypertune parameters and ran a couple of trials, and their average mean absolute errors are shown on the bottom right. Surprisingly, extra trees did better when the hyperparameters were tuned and multiple trials were run. My final model was the extra trees models using all 12 features and quantile transforming the non-solar features. The hyperparameters were MAE and N estimators being 75. I then reran the model with all of the training data, and the MAE on the test data was 700. This is lower than the validation error at the initial phase of the study and consistent with the validation error previously attained. However, it's not a great result in terms of the range of target values, which was 0 to 13,000. Future possibilities of study could be to look at the imbalanced target data and remove the records where the sun is off, because we know if the sun is off, there will be no solar generation. So it's a little silly to ask the model to run those results. Also, I would have liked to explore permutation and drop column feature importance to further investigate collinearity. Thank you.